It's not documented. There's a plot plan.
All right, we'll start. So today we're finishing stochastic local search algorithms, and then we'll start planning on Wednesday, having had a break for Family Day. So this is the overview, a couple of announcements. We're going to do a recap on stochastic local search, talk about various types of stochastic local search algorithms. There are many, many types. And there are many, many hybrids of types, so it gets confusing. And then we'll talk about a very important application, which was actually developed here at UBC on algorithm configuration, which is having quite an impact. And I thought I'd just talk briefly about some recent AI successes, just to keep you motivated and realize how important this stuff is in the world. It's making people lots of money. Okay, so announcements. As you know, it's a week today. Assignment 2 is due. I'm sure you have some midterms next week, so you've got lots of time this weekend. Unfortunately, it's going to be sunny, so that's a distraction. And our midterm will be after the break, on March 6th, here. It'll be 45 minutes long in the class slot. Okay? The structure of the midterm will be like this. There will be a set of short questions I will provide you ahead of time. I'll provide you all the questions without the answers. It's up to you to find the answers. And then some subset will be on the midterm itself. Plus, there'll be a question which requires some thinking and computing in your head. No aids will be allowed. It'll all be from your head. And I'll also provide you with a sample midterm of that flavor on Connect shortly. Okay? And they've just scheduled the final exam. Our exam is on April the 18th, Thursday, which I think is sort of in the middle of the exam period, which is nice. And I will schedule extra review sessions as much as you want. After the classes end, We've got a lot of material to cover, so we'll be going probably right to the last lecture, as you can see from the schedule, but I'd be happy to give 1 or 2 extra sessions. And there, the idea will be that you will tell me what you want to cover, what you want to review, okay? And it'll be completely sort of free form. Any questions on any of these? Any questions on anything? Yeah?
I have a question about the videos, the class videos. I know the server was down last night and this morning, and it was down several times.
Oh, okay. That's beyond my control. I can try and find out what's happening. It's been up until then. I mean, it's just... Has anyone else noticed this problem with the server? Looking at the videos?
It was fine this afternoon.
So it's working this afternoon. That's good news. Okay. So we'll keep an eye on that. Send me a message if that kind of thing happens. I can send a message to help, and they can bring it back up. How many of you have actually looked at any of the videos? Okay, just a few. I suspect there may be a few more before the midterm, I'm guessing. And certainly before the final. Do you find them useful? I mean, is it a good thing to be doing?
Yep. It's great to put them on your iPod for the bus.
Say again?
Put them on your iPod for the bus.
Okay, right. Good. Okay, that's useful. We'll keep doing it then. We haven't edited them. What we're planning to do is chop them down just so the irrelevant bits at the front and the back are chopped off and put them on YouTube eventually. But for now, they're just for your use, and we don't want them reposted. You can put them on your iPod on the bus, but that's fine. But don't put them anywhere else. Don't put them in any public place, please. What about the practice exercises? Have you tried those? Who's actually used any of the practice exercises? Okay, just a small number of you. I think you probably would be advised to use them. The kind of questions we put on the exam are the kind that you see in the practice exercises. Might even sneak one of those on the exam. Just reward those if they've tried them. So I really recommend doing them, and do them, without looking at the answer. Just do them and then check against the answers. That's why they're there, so you can do some self-learning. And in particular, the current one up is exercise 5, and it's really good stochastic local search. Since that's one of the questions on assignment 2, I suggest you do exercise 5 first, and then look at the answer, and then do, I guess it's question 4 on assignment 2 that uses the stochastic local search applets. Okay, any other questions? Okay, so we're going to just recap stochastic local search. If you had any queries about it, now's the time to ask them. This is sort of a new concept, maybe, this idea of a randomized algorithm. And so the time the algorithm takes on a particular problem is a random variable. It could go from 0.1 seconds to 3 hours, for a single instance of one problem. Okay, depending on which lucky guesses it makes. And so using the median is a good idea. The median time, that is 50% of the runs take less than this time, 50% take more. That's a good statistic. The median is resistant to outliers. If you've done any statistics, it's a robust statistic against outliers. If you have one really large number, it doesn't matter how large it is, you could double it, it still will have no effect on the median, right? But if you take the mean, which is the average of all the values, that really large number will shift the mean. So we want numbers that are robust against that. So median is one idea, but even better is to get these runtime distributions that show for a particular number of steps, if you fix the number of steps, then each of these, so suppose I fixed it at 11 here, no, that would be 20. If I fix it at 20, each of those 3 algorithms solve some fraction of the particular problem that we're working on. Okay, the green one got about 0.1 of them, and the red one got about 0.28, and the blue one got that many. Okay, so you can run them over and over again, and if this might have been on 100 runs, and we noticed that when we did this twice on the same problem with the same algorithm, we got a different runtime distribution. Only slightly different, but different, right? But if the more runs you test it on, the more it's going to converge on a particular version of this curve. Okay, so if you did it on 1,000,000 runs, I suspect you did it on another 1,000,000 runs and compared those 2 curves, they exactly correspond with each other, because these are just the fraction of solved runs in a particular set of, say, 100 runs, running up to 1,000 steps per run. So that's just the fraction of solved runs over that particular set of runs. And so it's not really the probability, but it's, as was pointed out before, it's a frequentist idea. And hopefully in the limit, as the number of trials goes to infinity, the frequency approaches the true probability that you will solve the problem. Okay? So these runtime distributions are a really powerful tool, and the applet computes them for you, which is nice. Okay, there are good things and bad things about stochastic local search. Again, I've hammered on this, but it's not guaranteed to find a solution if it exists. So you can't tell if a problem is solvable by using a stochastic local search, unlike using deterministic arc consistency and domain splitting. They stagnate, which means they get stuck in a particular portion of the search space and don't break out into other portions, particularly if you don't use random restarts. And then you can't tell what that means. Is the problem infeasible, no solution, or is it stagnating? Theoretical analysis is hard to come by. There is one nice little result, and it's actually worth relying on, that if you're using random sampling and random walk, there's a strictly positive probability of making n lucky choices in a row. So actually, this algorithm, random sampling, just sort of randomly choosing a point in the possible world space, and then randomly walking away from that, is guaranteed to find a solution if one exists. It may take longer than the lifetime of the universe, but there is a finite non-zero probability that you'll find the global minimum with that algorithm. Because for each time you're making a choice, there's some finite probability you're going to go in the right direction. So you multiply all those numbers together, they're going to be very small, but non-zero. Okay? But one of the positive things about stochastic local search is that you can use them as anytime algorithms. You can use the best solution found so far and then keep running the algorithm. You might find a better one. And the other thing is they're much more general than the arc consistency domain splitting algorithms because they can work on any optimization problem. We're doing it on constraint optimization, but we'll look at RNA secondary structure design as another application, which again was developed here. And another feature is they can work on dynamically changing problems, where the problem is changing as you're trying to solve it. Right? It's an online problem, airline scheduling. You've got a big blizzard coming into New York City. You've got thousands of flights going in and out. You have to cancel some fraction of them. What's the best way of rearranging the schedule to get the maximum number of passengers to their destinations? Right? So you've got an existing schedule. It's broken for some reason. Some resource is gone. You want to repair it. And you can repair it by making a minimal number of changes. You don't want to just generate some random, completely different schedule because you've got a fixed cost of changing any flight and any crew assignment and airport docking fee and all the rest of it, right? So for those kinds of problems, stochastic local search is also more useful than the arc consistency deterministic algorithms. And then we talked about, again, for generality, we can talk about constraint optimization, where instead of having all hard constraints, which we do in the standard CSP model, every constraint is equal and every constraint has to be satisfied. Or, a slight relaxation of this, we want to satisfy as many constraints as possible, but they're still all equal. You can do that in the SLS version. You can't do that in arc consistency versions. But we can go beyond that and go to constraint optimization, COPs, where you have a set of hard constraints usually and a set of soft constraints that are desirable to satisfy. And they might be in some hierarchy. You could weight them. Each constraint could have a certain weight, which could be the cost of violating it, say, right? And you want the minimum cost solution. And the hard constraints would have very, very high costs. And then H of m would just be the sum of the weights of constraints not satisfied in our current node in the search space. Okay? So, as I said, hard constraints have a very large weight. Some soft constraints can be more important than other soft constraints. It gives them a larger weight. And all the local search methods that we've discussed, that we have discussed and will discuss, work just as well for constraint optimization as they do for constraint satisfaction. You don't have to change a single thing. You're still looking for a global minimum, but you just don't care that it doesn't have to be zero anymore, right? Which is where they're all satisfied. You still want the global minimum. So, as an example, again, this is being done at UBC. Our exam was scheduled using constraint optimization developed by Holger Huss and Frank Hutter and that group in computer science. So the kinds of hard constraints is obviously every exam has to be in a room larger than the number of students in the class. You can't put two exams in the same room at the same time, so on and so forth, many others. And there are other things like student preferences. I mean, ideally, and this is a really important, but it's a soft constraint. I mean, if you have to satisfy all these. If you absolutely have to make one student write two exams at the same time, you can solve that by giving the student a separate exam the next day. But it would be nice if students didn't have multiple exams on the same day. It would be nice if the exams were spread out as much as possible, not all in a 3-day period and so on and so forth. And all of these constraints are built into the scheduler. And if you have any complaints, talk to Holger Huss. Yeah.
So by label them important and nice, how would you prioritize these soft constraints?
Well, you just have to assign a real number to each constraint. Okay? So how more important is this than this? Right? So and you say these hard constraints would have like, I don't know, 100,000 each, right? Just to make sure that any solution you come up with satisfies all of the hard constraints. And then if we have a choice between satisfying this one and satisfying this one, we want to choose satisfying this one. So we'd give it, I don't know, 500, whereas this one might be more like 50. So it's 10 times more important. And think of this as a cost. And we're trying to find a solution that minimizes the total cost for all the students and all the professors involved. Right? Okay, so as I said, you don't necessarily have to stop at constraint optimizations. You can optimize any arbitrary function as long as you can evaluate the function for an assignment of the inputs. Yeah?
Go back to this slide.
This slide?
For example, if the student is having 2 exams at the same time, they must have multiple exams at the same day. So there will be some overlapping during double counted weights.
Yes, it could be. Yeah, yeah. That's okay. But this one would dominate that one. So, there's a high cost to having a student having an exam collision at the same time slot. So any ideal, I don't know if any of you have ever found this situation. Probably not, because again, there's sort of a lot of locality in the scheduling problem, because most of you are taking mostly computer science courses, and you don't interact a lot with people in linguistics or in psychology. So, except if you're in cognitive systems, which you do. So there's all this locality will mean that you can actually usually satisfy all of the hard constraints and most of the soft constraints. But occasionally you get problems of having 2 exams on the same day or whatever, right? Or exams too clustered. But it's not a problem if a particular configuration doesn't satisfy both of these constraints. Okay, so you can optimize arbitrary functions. You don't have to be able to differentiate the function, for example. All I have to do is be able to, at a point, evaluate it in the search space, okay? And the inputs are our possible worlds. And so a nice example is secondary structure design for RNA, right? So DNA produces RNA, RNA produces protein. The shape of the RNA, the way the RNA molecule folds determines the conformance of the protein. So often you need to go both ways. You need to go from the RNA strand, which is just a string of 4 kinds of bases, right, to the secondary structure, but sometimes you want to go back the other way. Like given a secondary structure, you want to produce the RNA strand that could produce it, or predict from the RNA strand the secondary structure. Going this way is actually fairly easy. It's just a question of energy minimization, but there are some pretty good algorithms, especially if you try and lay it out in the plane. And some of these things, apparently, I don't know much about this problem, but apparently some RNA molecules will tend to be planar, and then it's really a lot easier. And so given that there are n of these bases, so the cytosine, guanine, adenine, and uracil, CGAU, shown here in the strand. And as it says, the 2 or 3D structure of the RNA folds is important for the function of the RNA. So given the strand, we can predict folding by just looking for a minimum configuration, and there's a low-order polynomial algorithm for doing that, order n cubed. That's an easy problem, but going back is typically, as in AI, this is like, it's the inverse problem. I talked earlier about inverse problems. So the graphics problem, if you have a 3D shape and you want to know what it looks like in 2D, that's a projection down. That's a very easy problem computationally. If you want to go the other way around from an image back to the scene, that's the vision problem, which is hard. It's the inverse problem. So here we have a direct problem, which is easy, and an inverse problem, which is hard. But we want to solve these hard problems, right? So typically you get all these interesting structures like these hairpin loops and various other, I don't know if you can read that even, but I can't really read it. There's a bulge there, and various external base here, an internal loop, and stacked bases, and so on. These structures will determine the kinds of proteins that will be generated by the RNA. So you may have a structure, and you want to say which RNA could produce that, right? So the idea is you do local search over the strands, right? So you might generate a random strand. From that strand, you can predict what its secondary structure is, And you can see how close that is to the secondary structure. That's your measure, your heuristic measure, H of n, how close it is in terms of matching the structure you're trying to generate. And then you could make some local changes to that RNA strand, generate new structures, and see if they're closer or not. And just use stochastic local search, right? Just, you know. So the evaluation for function for a strand is run the order n-cube prediction algorithm on the strand, that your current guess, and evaluate how different the result is from the target structure. So this H is only defined implicitly, but you can evaluate it by running the prediction algorithm. And actually, this is one of the best algorithms. It was at that time. I'm not sure if it's still the best, but it's certainly one of the best algorithms for producing RNA strands from secondary structure. It was developed by three graduate students, and Anne Condon, the department head, and Holger Huss. It's RNA SSD algorithm. So that shows this generality in one dimension. Another generality dimension is this idea of dynamically changing problems. As I said, you could imagine a schedule for an airline where you have thousands of flights and personnel, assignments, crew, and so on. And suddenly you get a storm which screws up some local portion of the schedule, and you have to take a whole airport out of the schedule. How do you rearrange it so that you maximally satisfy all the constraints, which include, you've got to have a certain crew for a certain flight, you've got to get an airplane to a certain destination in order to come back again, and so on and so forth. All those interesting constraints. So it's this idea of repairing the schedule with a minimum number of changes that you can do easily with stochastic local search. So you start from the current schedule, which used to be the optimum, but now you've changed the constraints, right? And so use that as a seed for your algorithm and start searching locally using all our techniques for SLS. And hopefully it'll come up with one that's nearby that would still satisfy the constraints, the new constraints. If you just use various other techniques like arc consistency, you need a lot more time, and the solution may require many more changes. Excuse me. So we're going to talk quickly about some stochastic local search algorithms. I thought I could get through this lecture without losing my voice. That may not be true. So we're going to quickly run through various, I can turn the volume up. So I'm going to quickly run through some stochastic local search algorithms. Lots of them we could spend a lecture on by themselves. We'll just look at them very quickly. You really don't need to know the details on these guys. There is a grad course occasionally offered on empirical algorithmics by Holger. There's a book on this which is available in the reading room if you want more details. So simulated annealing is an analogy to metallurgical annealing, where you heat up a metal, like steel or iron, to a high temperature. So you get a lot of random motion of the molecules, and then you slowly quench it. You slowly cool it down. So you want the maximum degree of order in the crystals that are formed. Okay, so that'll get the lowest energy configuration. So that's the analogy. You start with this high temperature. At the very high temperature, there'll be a lot of random motion of the molecules, right? So there will be a lot of random steps in the algorithm. As you cool it down, you will only take random steps that are not so bad. So when it's a high temperature, it may move to many worse states But as you cool it down, it'll only go to better states. So here's the detail. At some node, select a random neighbor. If the heuristic function of the neighbor is better than the node you're at, you move to the neighbor. You accept all improving steps. However, you may accept a state if it's worse than where you are. The higher the temperature, the more likely you are to accept nodes that are worse, okay? It'll depend on how much worse it is, the current temperature. And you make the probability of accepting worsening moves to exponential of the difference in the heuristic function divided by the temperature. And this temperature will be reduced according to an annealing schedule, as you do when you're annealing steel. Finding a good schedule is an art. So you can see if you check out this is the exponential of this function here. The higher the temperature, the higher the probability that you'll accept bad moves. As the temperature comes down, that probability will get smaller and smaller. Tabu search. So the idea of taboo is something that's forbidden, right? So in a taboo search, you don't want to go back to states you've previously examined, right? For example, it's a way of getting out a local minima. If you forbid the search from returning, to previous values, then it will be able to make further progress instead of getting stuck by going back over and over again to the same place. So basically you keep the last k assignments, variable value assignments, keep those as taboo, and then when you're thinking about taking a new assignment, you check to make sure it's not on the taboo list. So if you're at V7, if you change it from 2 to 4, you can't change the variable 7 back to 2 for the next k steps. And k is a parameter that you have to decide the best value for. Empirically. Iterated local search, these are all slightly different search techniques. So you perform iterative best improvement to get to a local minimum, and then you take a perturbation step. You take a jump, some random jump, not just a local random walk, but a big jump to get into different parts of the search space. One way to do that would be to take a series of random steps, like say a random walk, or use a short taboo search to make sure that you don't keep going back into there. You say once I've moved in this direction, I can't go back to these values. I have to keep going for k steps, which might be enough to take you over a local peak and get into a new basin of attraction. Another idea is essentially parallelism. Right? Now we've got multiple cores. Processes are cheap. Imagine keeping not just one best assignment, but k. K is a different k from taboo k. K assignments at once. That's like the beam width. You've got a beam of assignments that you're choosing instead of just a single one. And so when you're thinking of improving your k assignments, you take the neighborhood of all these k nodes, take the union of that, and that is your neighborhood that you're going to consider. And in the next step, you take the next k best neighbors that you're going to use. And again, you don't backtrack. So if you have your cards, if k is equal to 1, what is this? really. One of these algorithms we've already seen, greedy descent, breadth first search, or best first search. Talk to your neighbor, see if you agree. Okay, so question? You have a question? Okay. Gives me a chance to rest my voice. Oh, maybe it is. Thank you. Put flavor in it. That should do the trick. Thanks very much. Okay, so now that you've talked to your neighbor, am I going to throat lozenge? What's your vote here? Okay, so I see lots of blue. That's good. Yeah, this is just obviously greedy descent. We've got one best choice, always moving to the best neighbor. That's greedy descent. When you have infinity, an unbounded number of next nodes, unbounded parallelism. There's no limit on the number, on the width of the beam. What would you say it is? Talk to your neighbor, because I see some disagreement here. Okay, so what's your vote now? Anyone change their minds? Okay, it's really breadth first search, right? There's an unlimited width of the beam, but it's not penetrating. It's not like best first search, which is only applicable in A star, right? When you're going towards the goal. It's not doing that. It's still uninformed, breadth first. Okay? At step M, the beam contains all nodes M steps away from the start node, which is what breadth first search does. Okay? Expanding the whole level. So, of course, you can do a lot more parallelism now, because if you had K, you fix K, you could have K processors busy at the same time, each exploring their local neighborhood. You take the union of those, right? And then you get the K best of those, and then you go distribute those back to the processors, and so on, right? So it wouldn't be total parallelism. There's some serial bottleneck there, but you can effectively use processors that way. Okay, a variation on that is instead of just using the best neighbors, make the probability that the neighbor is chosen depend on the heuristic function n. So the lower the n, the more likely it is to be chosen, but not guaranteed. Okay? So the reason for this is often if you just choose the very best, you'll get sucked into a local minimum, right? But by allowing the not so good ones, which may be worse than even your current one, to have a possibility, but not a great possibility of being chosen, you have a chance of escaping local minimum. So experimentally, this kind of stuff seems to work well. Okay, so you could have it rank-based. You just order the nodes in terms of their value of h of n and have some fixed probabilities for where you are in the rank as to whether or not you get chosen. And the idea here is just maintaining of diversity among the nodes. So we're starting to get into biological metaphors. This is like asexual reproduction. You've got this node, and it's generating some successors. The likelihood that the successor survives depends on how good it is, but just because you're the best doesn't mean it's guaranteed. You might meet a tiger, right? So it just gives you a likelihood that you will survive. The mutations will survive, and the fittest tend to survive. Going even further, we can go on to sexual reproduction. So this idea of genetic algorithms. So it's like stochastic beam search, but you actually take a pair of nodes and swap their characteristics, right? It's like swapping chromosomes. So this is the algorithm. For each generation, choose pairs of nodes M1 and N2, called the parents, where nodes with low heuristic value are more likely to be chosen from the population. For each pair, perform a crossover, create offspring combining parts of their parents. And what we mean by crossover here is crossing over the values. You mutate, and then you put in some randomness, genetic variation, mutate some values for the offsprings, and select from the previous population, all the offsprings, which nodes to keep in the next generation. Okay? So this would be a crossover example. If I've got two nodes with these bindings for the variables, you just select some point I to chop the first node and swap the values for the first node up to that point with the values for the second node up to that point and get two offspring. Okay, so we've swapped the values. The A values here came from there, and the B values came from there. Okay, so again, this gets you into different parts of the search space, but it's combining some of the earlier attributes which you may not want to throw away. There's all sorts of other crossover operators that people use. That's a huge research field and has appealing biological metaphor, but it doesn't, again, it's very, very hard to analyze theoretically. But it seems to work for some problems well. You know, it's just one of these experimental things. And we don't have good theory for it. One really nice application of stochastic local search is almost applying it to itself. So this is like meta search, okay? So in stochastic local search, we've got a huge number of parameters, okay? For all these algorithms, say choose this parameter k, choose this probability, choose this scaling factor, et cetera, various kind of value and variable selection heuristics, percentage of random steps, restart probability. You know, as you do assignment 2, you'll discover there's a lot of parameters you have to set in these algorithms. In Tabu Search, the length of the search, iterated local search, what kind of perturbation are you going to do, what kind of acceptance criteria will you accept a perturbation. In the genetic algorithms, what's the population size, the mating scheme, the crossover operator, the mutation rate. And then you can hybridize all these algorithms, have pairs of them working together. Gives you even more parameters. So how do you choose good parameters? And this is not confined to this problem, but in general in computer science, we have lots of magic numbers in our programs. And there's sort of a black art to choosing good numbers. You can actually turn that problem itself into a stochastic local search problem. So you can apply stochastic local search to itself. You want to find the best values for the parameters, right? So this is what's called the algorithm configuration problem, and Frank Hutter did his PhD on this here a while ago. Here's the formal definition of a problem. You've got an algorithm that you can run. It's got some magic numbers, technically called parameters, and they have domains. You can set them in. You have some class of instances that you want to run the problem on. And you've got some performance metric, which might be runtime, or it might be space, or quality of solution, or whatever it is, some arbitrary metric, some real number, that says when you run the algorithm with particular values for the parameters on the benchmark set, you get some number here, how good it is, right? So what we want to do is define the parameter setting, which is called a configuration, of the algorithm that optimizes this performance metric on this class of instances. Okay? So you might have a whole bunch of different exam scheduling problems, right? And you have a whole bunch of different algorithms, and each of the algorithms has a bunch of parameters. You want to figure out what's the best one to use. So as long as you've got some way of measuring the goodness of the exam schedule, or how long it takes to find an exam schedule, or some combination of those, then you can use this formulation. And what basically comes out of this is that you've now got a way of automating the configuration of algorithms for applications in different domains. Instead of doing that manually, which requires hundreds of hours, and you probably aren't as good at doing it as a computer is, then you can get very good solvers, say for hardware configuration or software configuration, finding bugs versus finding bugs in hardware, using the same algorithm but customized in different ways, because the class of instances would be different. Okay? Does some wonderful things. And you can apply it to all sorts of problems. You can apply it to satisfaction, mixed integer programming, timetabling, probabilistic reasoning, protein folding, AI planning. Because we have all these different parameterized algorithms, right? With all these different possible parameters. So if you're doing this manually, and this is typically how we do it, you start with some configuration, you change some single magic number. If it gets better, then you keep the new configuration, change another number until it's good enough, right? But by changing the numbers one at a time, you're probably not going to find the best result, right? Because you need to do it in a multi-dimensional space. So that's really just a manually executed local search. So in these papers here, they talk about ParamILS, which uses iterated local search in parameter configuration space. Where this is the parameter configuration space that we're searching, and this is the value of the metric, doing that automatically. And here's another example of using it for mixed integer programming. I talked before about linear programming. So in integer programming, you want to minimize some linear combination of the variables, right? That's your metric here. This is just a row vector times a column vector to give you a number. You want to minimize that criterion given a set of linear constraints on the variables xi, and the xi all have to be integer. That's integer programming. It's a very standard problem. Mixed integer programming is just integer programming with some of the variables being integers, others could be reals. This is a hugely important problem, and probably the best solver in the world is this MIP solver that IBM, so developed by Cplex. iLog bought Cplex, and then IBM bought iLog, and they exist in Czechoslovakia, running, well, the old Czechoslovakia. Huge usage all over the planet for all these kinds of problems: transportation, logistics, supply chain management, production planning and optimization. By using mixed integer programming on those kinds of problems, they were able to get up to 50-fold speed up. And given that the kind of hardware iron you're running these programs on is very, very expensive, those large servers, these are massive, massive problems with millions of variables, that's enormous economic payoff using this ParamILS approach. Okay, so we're finished local search. These are your learning goals. You know how to do all these things now. At least you should. If you don't, you should read the book some more, do the exercises, etc., etc. And then at the end here, I just threw in some cool stuff about recent successes in AI. You've probably heard about Watson, which a couple of years ago beat the world champions, the all-time Jeopardy champions, using AI techniques. There's a lot of links here. You might enjoy looking at the links, looking at the videos. But the main point is to see that this really instantiates. From lecture 1, we talked about building agents, and Watson has all of these components put together. And now, they didn't really want to win at Jeopardy. They just thought that was a great way to get good PR, and they interviewed me and so on. And they managed to exploit the media successfully to market this. But now what the real markets are in legal reasoning and in medical reasoning. If you could have a lawyer or a doctor talk to a computer and say, this is a case I'm working on, give me the 10 closest cases with precedence, right? That's a big win, right? Same with doctors. So all these different components here fit into the agent model we were talking about. And the other big win is Siri, which actually came out of a project called Kalo, which is funded by DARPA. And maybe 500 person years went into developing Kalo in the DARPA project, which of course the Army is very interested in this PAL project, the personalized assistant that learns. If you had in your phone your personal assistant, which knew all about you and knew about your constraints and your plans and your bank account and your friends and everything else, a bit scary concept, but people, you guys don't seem to worry too much about privacy and all that stuff. Who cares? Google and Apple have all this information on us, right? If you're willing to give that away, then, because Siri doesn't run on your phone, right? It runs on this Apple servers, then there's big benefits for you and for Apple, by the way. So I just put a few things on here that struck me as cool about Siri, but it's just showing that what's happening in AI now is that the stuff we've been working on for 30 years is getting to the point where it's making a big, big impact. So the ParamILS work with the MIP solver, Watson, Siri, and so on are making a big difference in the world. Okay, we're done. Have a good weekend.